Welcome everyone. I am Kailash, a PhD scholar from Nano DC Lab IIT Gandhinagar, and this is the live session 4 of digital circuits. And we have this session every Tuesday from 6 p.m. to 7 p.m. In this session, our main goal is to discuss some of the concepts, some of the questions, doing your assignments, or will be helpful in understanding the concepts of digital circuits. Okay. As of now, what we have done in the previous lectures is we have discussed a couple of topics and questions of couple of topics like introduction to number system, Boolean algebra, combinational function, minimization using K-map and Boolean identities. Along with that, we have also discussed various questions on logic gates in the last meeting, right? So. In today's class, what we'll be doing is we'll be discussing about the multiplexers, decoders, and some of the questions on the basis of that, right? So we'll be having two sessions before 31st. So the half part will be done today, and the next part will be done in the 30th session, such that we should complete all the basic questions on multiplexers, decoders, and how multiplexers and decoders and arithmetic circuits can be solved. Okay, so let's start. So before proceeding, actually, I have not put many questions on multiplexer, but what I have done is I have some slides, two slides on multiplexers as universal gate. Okay, so we have heard and we know that okay, our this NOR gate and NAND gate are universal gate, right? But do you know that multiplexer is also an universal gate? Okay, and if you understand that, if you can design all the gates using multiplexer, you can virtually design all the circuits, whatever complex circuit you have using multiplexer, right? So the very first part of this today's session is to design all the basic gates using multiplexer. Okay, I've given some of the examples, starting with the very first example, and the most basic gate of digital circuit is what we call as NOT gate. Okay, so everybody know that this is the truth table of NOT gate. Okay, where you provide input at x and you will get the complement of x. Okay, so f will be x bar, right? So this is what we are designing. So what we are doing here is we are using a two input or 2x1 mux for designing a multiplexer. Okay, so how do you design, right? So the basic concept that can be used, you write the equation of multiplexer. If I write the equation of multiplexer, f is it will be x bar into I0, right? So I0 is the first input, then plus x into I1. Okay, what I want, if my x is an input, if my x is an input, I want that x bar should be the output. So for that, what I can do is uh, I can make this part as 1, right? If I make this part as 1 and this part as 0, okay? So what will be the equation? The equation will be f equal to x bar only, right? Because the other part will become 0, right? So now if you put x here and if you fix the first input as 1 and the second input as 0, uh, it will virtually behave as a NOT gate, right? So it will behave as a NOT gate. So multiplexer can be easily used to design a NOT gate. Any question in this concept? How we have designed NOT gate? So what we have done, we have taken 1:1 multiplexer. X input has been provided as a select line, and in the two of the inputs, if I put 1 and 0, this will behave as a NOT gate. Any
Sir,
question?
how we can yes, sir. How we can obtain sir expression for NOT gate by using K-map?
For NOT gate.
Yes, sir. You write f equal to x bar I naught plus x into I1.
Yes.
So yes, expression where we get
Yeah,
from this
this
expression.
is basic expression how multiplexer works. Okay, so let me explain you the concept. So I am not discussing the introduction, but let me tell you how the multiplexer actually works. So major goal of the multiplexer is to choose between two. Okay, so you have some option and you choose between two, right? So if I tell you on the basis of algorithm, how it will look like is, if I have something, right? If condition is true, right? If condition is true, do something, right? Else, do something. Okay. So this is the concept in which multiplexer works, right? In digital circuit, how it works is, if I provide, say, one input, okay? Suppose x is my input. If x is equal to 0, right? You select something, and if sorry, yeah, else part, else means x equal to 1, right? You select something else, right? In this case, what we are doing is, if x is equal to 0, select I0, right? Else select I1. Okay, so if x is 0, then select I0, right? If x is 0, select I0. So for this thing, right, you can write an expression like, if x is 0, then select I0. It means the value of x should be 0, and you have to select I0. If you write like this, I0 won't be selected, right? Because x is 0 and it will be multiplied by 0, it will be 0. So what you can do, you can put a x bar, right? And if you write something as f equal to x bar I0, it means whenever x is 0, f equal to x bar, right? Whenever x equal to 0, f equal to I0. So that is the first part. And similarly, if you want to select I1 when x is equal to 1, you can write x I1, right? So whenever x is 1, right, what is the expression of f, right? If I simply write like this, okay, whenever x is equal to 1, I select I1. And what I've done, I've just combined both of them, x bar I0 plus x I1. So you can use a k-map, but this is a very simple approach by you can design a multiplexer, or you can write the expression of a multiplexer. Is that clear?
Yes, sir. Sir, please use K-map. Please explain about using K-map.
So you want using k-map?
Yes, sir. Yes.
That's also can be done. So how many variables we have here? Anyone? How many variables we have? One variable. No, it's not like that. No, not two. We have three variables here. Okay. So what are the three variables? The two
Zero
input,
I1
I0, I1. The
and
other one is
X. Yes.
this is my select line. That is there. Okay. So 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. Okay. So the function of multiplexer is, if uh, okay, just uh, give me 1 minute. So if x is 0, what you have to select? You have to select I0. So let me write down the combination, right? So let me make a table like this. Okay, so x I0 I1. Okay, so see, 0 0 0 0 0 1 0 1 0. Let me write somewhere else. Okay, so because what you have to put in KMF, you cannot directly think. If you cannot think like that, you can write a expression x I0 I1. Okay, and this is my f, 0 0 0 0 0 1, then 0 1 0 0 1 1, then 1 0 0 1 0 1 1 1 0 and 1 1 1, right? So if x is 0, so this is the part, right? What will be my f? If x is 0, it will be I0, right? So it will be 0 0 1 1, so whatever the value of I0 it is, and if x is 1, right, the value will be I1, so this will be 0 1 0 1. Okay, so let me see on which places we have 1. So this is the one, so 0 1 2, then 3, okay, 4 5 6 and 7. So okay, 2 3 and 5 7, right? So let all of this here in the different color. So this will be 0 1 0, so 0 1 0 is this one, then 0 1 1, so this one, okay, 5 1 0 1, this one, and then 7 1 1 1, this one. Okay, so now what you have to do is you have to combine this. Okay, so if you combine this, you see you can combine this and combine this. Okay, so if I write the expression of this f equal to, for the first part the expression will be x bar. Okay, x bar, and what is the variable that is common here? This is I0. Okay, similarly for the second part the variable is x, and what is the variable common here? That is I1, right? This was the expression I've written.
Okay, sir.
Is that clear now?
Yes, sir.
So this is the long way by which you can do. But yeah, this is the universal. If you don't understand, or if you're stuck in somewhere, you just go to the K map, and for the K map, you just write down the truth table, and on the basis of that, you can directly write down the equation. Now, okay. So now, for the NOT gate, did you guys understood how I have designed a NOT gate out of it from this expression? Now, because you know that how this expression works, right? Yeah. I believe you guys have understood, right? You can type yes in the comment section such that okay, I know that you have understood. Okay. So now what we will do is we will design other gates. Okay. So let me write this equation here over there. X bar I0 plus X I1, right? And using these two lines, what you will do is you will write programs. Okay, so now what you have to do is you have to do design an AND gate, right? The AND gate is the expression of AND gate is when the input is 1 1, okay, the output is 1, right? So you see here is this part looks like an AND gate, right? So if I put X as A, right, and I1 as B, okay, or here what I've used X and Y, right? So X as small x and I1 as Y, right? And if I somehow remove this term, right, this will be what? This will be XY. Right? That's very simple, right? So I know that okay, for I1 I have to put Y, so I put Y here, right? And how to remove this term? I cannot change x, but I can write I0 as 0. So I put I0 as 0, and this will behave as a AND gate. Very simple, right? So f equal to xy. Is that clear, students? Is that clear? Okay. So now, okay, Gulshan wants to repeat again. Okay, so yeah. So let me repeat again. So what I want is to design an AND gate. Okay, what I want is to design an AND gate, and for designing an AND gate, what I have to do is I have to come up with this equation x y, right? This is my AND gate, right? Now what I have to use a 2:1 multiplexer for designing an AND gate, right? So I know that the equation of AND gate is f equal to x bar I0 plus x I1. Okay, and if you look at this part, right, if I keep x as x, right, and I1 I put as y, right, this will be an AND gate, x into y. But the problem is this part is additional. Okay, so I have to put something to remove this particular part. Okay, so to remove this part, if I put I0 equal to constant 0, right, so what will be this? This will be x bar into 0 plus x into y, right? So the I1 I have put y, right? I0 I put 0, right? And I put x, right? And you write this equation. This equation will be equivalent to xy. So this will behave like an AND gate. Is that clear?
Yes, sir.
So now moving to OR gate, right? So because you have lot of questions in the assignments, and you will get this kind of questions in your interviews, in your exams. Uh, how to design multiple logics using 2 is to 1 multiplexer or 4 is to 1 multiplexer. So you should remember this thing. Okay. Now what I want to do, I want to design an OR gate. Okay. So if I want to design an OR gate, this expression I want 0 1 1 1, right? So what I want is f equal to x plus y. Okay. So let me write the equation again for you. So this expression is f equal to x bar I0 plus x I1. Okay. So so I need x plus y. So I know that, okay, this part I need x. So here what I will put is uh, I will put I1 as 1, right? So this if I put I1 as 1, so this will be x bar I0 plus x, right? So this everybody know. And if you know that you can write this expression as x plus x bar into x plus I0. Okay, so this is the distributive property. Okay, x plus x bar is 1, so this is x plus I0, right? Now what you have to do, you have to just put I0 as y. So if you put I0 as y, right? So if you put I0 as y, so here I put y, this is 1, right? This will be x plus y. Very simple. So this will behave like an OR gate, right? So the same concept, or same 2 is to 1 multiplexer is being used uh, as NOT gate, as AND gate, as an OR gate. Okay. Now what we will do, we will go to getting more complex gate. You require more complex uh, more complex things, right? So can anybody tell me what the first diagram will do, and what will be the output of the first or the first this first part, right? Which gate it represent? Anyone? Please note that the first one is NOT gate, right? So because we have discussed that this is how NOT gate is being defined, right? Anybody wants to answer? NAND. Okay. From Gaurav, he is saying that this is a NAND gate. What about others? So what I will do, I will try to solve this because this is a NOT gate, right? I won't explain that how it is a NOT gate. So you know that here it is y bar. Okay. So one of the input is y bar over here. Okay. And if I write the equation of this particular gate, so it will be f equal to, right, x bar y bar, okay, plus 0 into x, right? So this will be x bar y bar, and this will be x plus y to the bar, right? So this is not a NAND gate, rather this is a NOR gate. Everybody is clear on this part?
Yes, sir.
Now quickly I will go through all the gates, right? So repeat, okay? Let me repeat again. Okay. So everybody please listen carefully, right? So this is the NOT gate, right? Because we have seen here, right? So this is a NOT gate. You see, 10x. So here 10 it is y. So it instead of x bar it will be y bar, right? Y bar. And I'm doing nothing, right? I'm just writing the equation. You write the equation f equal to x bar. So x bar I0 plus x I1, right? So this is the equation, right? And now I will put the value of I0 and I1. Okay. So x bar I0 is your y bar plus x I1 is equal to 0. So this will be, so this term will be gone. So this will be x bar y bar, right? And you can apply the De Morgan's, right? So this will be x plus y to the power bar, right? So this is x plus y bar. So this is an OR gate. the next part. Okay. Anybody wants to give me the answer of this gate? Anyone? So this will be y bar. Very simple.
XOR gate.
XOR gate. Okay. Let's try and let's understand if it is an XOR gate or not. Right. So what it will be? It will be x bar, right, times 1 plus x into y bar, right? So this will be what? This now you can write this like, so x bar plus xy bar. Again, you can apply the distributive property, right? So you can write like x bar plus x multiplied by x bar plus y bar, right? So this, this is a distributive property, right? Yeah, it's a NAND gate, right? So this it will be x bar plus y bar. So f is equal to x bar plus y bar, right? So this will be x dot y to the power bar, right? So this is a NAND gate. Now, if I move to this part, this gate, anybody wants to tell me what gate it is? It is XNOR. Gaurav is saying that this is XNOR. Anybody else?
It's XOR.
XOR, okay. So I have two options, XOR and XNOR, okay. XOR, okay. Yeah, everybody is saying XOR, okay. So three decision. So it should be XOR. Let's see. Okay, so this is the Y bar, right? Very simple. Okay. So now this is X. So if I write the equation F equals x I0, sorry, x bar I0 plus x I1, right? So this is the basic equation. I will put the value of, uh, sorry, I will just put the value of I0 and I1. Okay. So if I put the value of I0 and I1 here, so this will be x bar y plus x y bar, right? So this is an XOR gate, right? So good. So only one gate is left. So I hope this will be an
XNOR.
let us see, right, if it is an XNOR gate or not, right? So without solving, I don't believe that, okay, this can be an XNOR, but let's see. So if I put y here, so this will be y bar. So if I write the equation directly, I hope now up to now I should not write the basic equation. So it will be x bar y bar plus xy, right? So this is the equation of XNOR, x bar y bar and xy, right? So what we have done here, we have solved seven circuits, not eight, seven. And using multiplexer, now you understand how to design any of the gate, right? So in assignments, in any of the exam, the questions can be asked, right? You write this equation using multiplexer. Now you just have to fit in values to appropriate terminal, and what value you have to fit, you have to decide, right? And you can design a logic. And similarly, if you have given a circuit based on multiplexer, you write down the equation, you put appropriate value, you will find out whatever the equation it is, right? Whatever the logic it is. Is this part clear, everyone? I need yes from you. Okay.
Yes, sir.
Yes, sir.
Thank you. So let's move to yeah.
Sir,
Yes.
sir, can we implement logic gates using 4x1 mux also?
Yes.
Is that possible?
Yes. You can, if you can use design using 2:1, right? You can use it using 4:1, right? We will see some. So I have one question using 4:1 marks. So let's see over there. Okay. So how 4:1 can be used? So the very first question is, it's not a MCQ. Uh, so the question is, design a binary to gray code converter using 2:3:8 decoder. Okay. So this is the question. How to approach this question, and other way around, it can also be given that, okay, this is the circuit. What does it do? Okay. So for understanding, okay, what is binary to gray conversion, right? I have written down the truth table for you, right? I hope everybody knows, right? So the binary code is like this, and this is how the gray code look like. Okay. So And please note, one of the important property of the gray code is between every two successive number, there is change of only one bit. It means, so there is change of only one bit. It means you see there is only one bit is flipping here, right? If you go from this part to this part, this remains same. This part and this part remains same, right? And yeah, there is only one bit, right? So similarly, for all the bits, only one bit is changing, right? So that's the unique property of gray code used in many places. Now we have this truth table and we have to design. Okay, so we know that okay, this is a gray code, that is the reason why it has been written as a gray code converter. But you could have been asked that okay, this is the truth table, right? You design a circuit which converts the first part, so the from the first part to the second part, right? If I provide say 101, it should give me 111, and it should be designed using 3 to 8 decoder. Okay, so let me design a 3 to 8 decoder for you, and I please let me know if you don't understand anything. Okay, so I will write 1 2 3 4 5 6 7 8, right? So this is how it looks like if I write uh, so if I write I0, I1 and I2, right? So here it will be O0, O1, O2, O3, O4, O5, O6 and O7. Okay, anybody? So you have 8 outputs, so for each of the output you will have an expression, right? So what expression you will have for O0? Anybody wants to tell me?
Not plus I1 bar plus I2 bar.
I0 bar plus I1 bar, you're saying this expression. Anybody else?
I0 bar, I1 bar, I2 bar.
So it will be like this. Okay, it will be I0 bar, I1 bar and I2 bar, right? So O0 will be 1 if the input pattern is been provided as 0 0 0, right? So if you provide 0 0 0 in all of these three, it will be 0 0 0, and 0 bar 0 bar 0 bar, it will be 1, right? Similarly, you can write O1 equal to I0 bar, I1 bar, I2, right? O2 equal to I0 bar, I1, I2 bar. Okay, so O3 equal to I0 bar, I1, I2. Similarly, O4. This here, this expression you can write from the truth table also, but we know that okay, I have to convert a number, right, the binary number into one of the lines, right? So I can directly write the equation. So you can write I0, I1 bar, I2 bar. Similarly, O5 equal to I0, I1 bar, I2, O6 equal to I0, sorry, I0, I1. Uh, I have done some mistake. No, I think it is fine. I1, I2 bar, and O7 is equal to I0, I1, and I2, right? So this is how the decoder look like. Okay, so what I will do now, I will. Any problem here? Okay, so now what I will do is I will design two decoders. Okay, uh, so let me just copy. Okay, let me just copy this. Okay, so see, if you give 0 0 0, what is the expected output for the gray code? It is 0 0 0, right? So if you have to design a binary to gray converter, you just have to connect the appropriate lines. Okay, but the second should be okay. So the thing is, the question should be not like 3 to 8 decoder, rather 1 3 is to 8 decoder and 1 8 is to 3 encoder. Okay, so it should be like that, right? You cannot design using 2 3:8 decoder. Okay, so if I design the encoder over here, it will be like this, right? So this will be your final output. So this will be my G0, G1, and G2, right? So I will have 1, 2, 3, 4, 5, 6, 7, 8, and you will have similarly I0, I1, I2, I3, I4, I5, I6, I7. Okay. So now what you have to do is you have to just make sure that Z0, G1, and G2 should be high, or the input pattern provided is 000, right? So the thing is, for 000, the gray code is 000, right? So what you can do here is you can directly connect this to this. Okay. Now if you understand this, for the next part, for 001, the input combination for the next part should be 001. Okay. Now the challenge is here, right? So 010, what I want the output as 011. Okay, so for 010, the output should be 011, right? So this is my 011. I will just write, okay, 000, 001, 010, 011, 100, 101, 110, 111. Okay, let me choose another color for you. After that, for 011, it should be 010, so it should be 010. Okay, so let me move to that again. For 0100, it will be 110. So for 100, it should be 110. Similarly, for 101, for 101, it is 111. So it should be 111. For 110, it should be 101. So this will be 101. And for 111, it will be 100. So it should be 100. So this is the circuit that is a binary to gray converter using 1 3:8 decoder and 1 8:3 encoder. And how it is working? The working is extremely simple over here. What you are doing is you are giving an input, right? You are decoding the output from here, and what you are doing is you are just connecting the output to appropriate line such that the output should behave as a gray. Okay, so for this encoder, you're not giving the output in the form of binary, rather you are giving output. When you will provide 000 here, the 000 will be activated and the output will be 000. Okay, but when you will provide 111 here, right? So when you will provide 111 here, this output will be activated, so that is fine. But for here, it will activate this line, right? And when you activate this line, this will output 100, right? And similarly for all other pattern. Is this concept clear, or is this question clear? How you use one encoder, one decoder to design a binary to gray converter?
Yes, sir.
Yes, sir.
So moving to the second question. It's a very simple circuit. I want that everybody please see the circuit and let me know X here and Y here. You can write down this is a multiplexer. Okay, this is a mux. There are two mux, and this is 4:1 mux. Sorry, yeah, 4:1 mux. It has two select lines. Okay, for 4:1 mux, I can write down the equation for you. So for X, it will be the input lines are A B, right? So A bar, B bar, right? So if this is I0, this is I1, this is I2, and I3, right? So this will be I0 plus A bar B I1 plus A B bar I2 plus A B I3. Okay, similarly for Y, it will be again the same. So I will just copy it. See how to solve this problem. You write down the equation. If you write down the equation, half the question is already solved. Okay. And what you have to do? You have to just put the value of I0, I1 and I2 and I3. Right? Anybody want to tell me what X is and what Y is? Anyone? So what will be the first term? A bar, B bar and
Okay.
C
C.
plus A bar B, C bar plus A B bar plus A B C. Anybody know this four terms? What does it make?
Sir, I have a confusion here. Sir, with I2, will there be AB bar or AB? Okay. Okay, sir.
Anybody know what it is? If you don't know, this is A XOR B XOR C. Everybody agrees this is A XOR B XOR C, or should I have to explain?
Yeah, sir.
So
Fine.
please explain once.
We should explain. So, okay. So, there is only two steps what I have to do. Okay. So, see, uh, from here, what I will do, I will take C bar common. Okay. C bar, A bar B plus AB bar. Okay. Then plus, from here, I have to take C common. Right. So, here it will be A bar B bar plus AB. Right. So, this is what? This is C bar A XOR B, right, plus C A XOR B bar, right? Should I explain it further, or you have got the answer? This will be, what is this? A bar B plus A B bar, right? So this is C XOR A XOR B. Everybody agrees?
Yes, sir.
Yes.
Okay, sir.
So see, the first part is A XOR B XOR C, right? Let's see what is the second part. Anybody wants to tell me what is the second part?
A XOR B into C plus AB.
So let's see. So what you are saying is A XOR B into C plus AB, right? So this is a very familiar equation for me, but let me see if it is like that. Okay, the first part is 0, so I just drop it. The second part is A bar B, so A bar B C plus A B bar C plus AB. Okay, so this is correct. So this is A XOR B. I take C common plus AB, right? So this is the first expression A XOR B XOR C, and this is the second expression A XOR B into C plus AB. Can anybody tell me combine what this combined circuit is doing?
Adder
Full
circuit.
adder.
Full adder. Full
It is
adder.
a full adder, right? So you have used two multiplexer to design a full adder, right? Isn't that great, right? So using multiplexer, you have designed the full adder. So now you understand, right, why I have discussed using multiplexer, how to design basic gates, right? And after that, what we have done, we have designed multiplexer using 4 is to 1 multiplexer, right? So moving to next question, this is the third part, okay, third question, and you have to tell me that, okay, what does this circuit represent? Okay, so this is a decoder over here, right? So this is a 2 is to 4 decoder. So you have to give me the expression of F. So you can ignore enable for now, right? Because it will only work when enable is 1. Anybody wants to try and want to give me the answer? I will write it for you. So this y0 will be what?
It may be S0,
Yes,
S0 bar,
0 bar, S1 bar.
S1 bar. That is ANDed with W0. So the function f has a first minterm as S0 bar, S1 bar, W0.
Second minterm.
Second minterm will be S0, 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 S1 bar,
S0 bar S1.
bar, S1, W1
Okay.
plus S1 bar, S0,
W2.
W2 plus S1, S0, W3.
What this equation represents? Anybody wants to tell me?
Multiplex.
Right. So it is 4:1.
4:1. 4:1 multiplex.
So just we have seen in the previous slide, right? So this is the equation, right? So see, using decoder and AND gates, we have designed multiplexers also. So I'm giving you all sorts of questions by which you just understand the concept. Yeah, any question?
No, sir, no.
No questions, right? So this was the third part. Let's move to the fourth question, which we have. Right. So the question is very simple, and it was a fill in the blanks question in one of the GATE exam, right? But I again given the options for you, such that you can tell me that if there are m input lines and n output lines for a decoder, okay? I have a decoder, right? So this is my decoding logic. This is my decoder, right? It has m inputs, okay? So it has m inputs and n outputs. Right, that is used to uniquely address the byte 1 kilobyte of RAM, right? So 1 KB of RAM, it is actually this decoding logic is actually addressing 1 kilobyte of memory, right? So 1 kilobyte is 1024 byte. Okay, so what it has been asked is what should be the minimum value of m plus n? So you should tell me m also, and you should tell me n also. Okay. Anybody else? See, where the decoders are used, you should know, right? So decoders are generally used for addressing, right? As an address, so you give the address, the decoding logic will give you the corresponding output. So if you use say 2:4 decoder, what you are actually doing is you are giving 2 inputs and you are taking 4 outputs, right? Similarly, if you are giving X decoder, you are giving X input, how many output you are taking to the power X, right? So here it is saying that, okay, I have to address a memory, right, which is 1024 bytes, right? So I have a memory like this, each of these are like this, right? And I have 1024 lines, 1024. Okay, so this all 1024 will be connected with the output of the decoder. So what does it mean? It means that the decoder has 1024 outputs. And to address 1024 output, how many input you require?
10.
1034, third option. I hope so.
So third option 1034.
Yes. right? So this kind of question can be asked because this is directly application, right? You know that okay, there is a decoder, right? But where to use the decoder? So decoder has to be used somewhere where you provide some address of 10 bits. It will make high one of the lines, right? And this one line can be used for the memory to access one of the rows from the memory. Okay, so for here the answer is 1034. Now I have one more question for you. So the question is, this is my truth table. You have to tell me which logic it is, right? So is it a priority encoder, it is a decoder, it is a multiplexer or demultiplexer, right? So I have four inputs, D0, D1, D2, right? And I have two outputs, X0 and X1. Valid is a case that, okay, if valid is 1, then only you should take the input. So you just have to focus in this part.
Priority encoder.
Priority encoder. Why do you say that?
So we are considering only the most significant values, the one.
Okay. Most significant one. Okay. Correct.
Yes.
Right. So what is the dimension of this encoder? X is to Y. So what should be X and Y? Like that. It is 4 is to 2, right? 4 is to 2 encoder. Right? Because I have four inputs, two outputs. So everybody know that. Okay, this is 4. Right? Now the thing here is it is an encoder, we know, right? So because it is encoding something, it is taking 2 to the power n inputs and it is giving me n outputs. Okay, so this is an encoder. So three options are already removed. Okay, so the only option will remain is priority encoder. But the thing is, why priority over here, right? You see there that if you provide a pattern which has 1 in it, okay, 1 as MSB and all zeros, so you will get the encoding as 00. But what if I have provided like this 11000, right? Even if you provide 11000, right, the priority has been given to the first part or the first MSB, right? I think MSB is this. Extremely sorry, right? So if you see here, it's other way around. Okay? So you have to go down, right? So you see, if one is detected as the at the MSB, so this is my MSB, right? It doesn't matter what our other bits are. It doesn't matter what other bits are. If one is at MSB, you will get the output 1 1. Okay, so it means 100 you provide, the output will be 1. Even if you provide 1100, right, still the output will be 1, right? Despite 1 has been encoded here, but because this one has been given the priority, right, so the output should be 1. Okay, now the thing is, I've given you truth table, you know the answer that this is a priority encoder. Before the next class, right, you should just take a screenshot of this thing and it will be uploaded into YouTube also. You just write down the equation of x0 and x1 for this particular case, for the question 5. Okay, everybody will do that,
Yes, sir.
right? So you use a Karnaugh map and just write down the equation that what will be x0 and x1. Okay, so the answer here is priority encoder. So this was the last.
X0
Yes.
D3 plus D2.
Sorry.
X0 D3 plus D2.
What you are saying, x0 d3 plus d2.
Yes, X0 is equal to D3 plus D2. And X1 becomes D3 plus D1 D2 bar.
Okay. X 1 minute. 1 minute. X0 is equal to d3 plus d2, and x1 is equal to what?
D3 plus D1 D2 bar.
d3 plus d1 d2 whole bar.
No, sir, it's only for D2.
Only d2 bar. Everybody agrees with this? So I suggest, or I will not solve it here for today, right? But I suggest what you do. So this expression has been given by one of the students, right? But the thing is, you just go, you solve it, and you come back in the next class, which is on 30th, right? Before the assignment deadline. That okay, if you are able to come up with the equation for this particular triangle. Okay. And similarly, one of the more other thing which because I have taught you, right, how to write the equation for multiplexer, right? Similarly, how to write the equation for decoder, right? So what you have to do, you have to write the equation for demultiplexer also, and you have to write the equation for encoder also. So write demux and encoder, right? And what you can do is you just take this any of these circuits, and you just think, okay, if I want to design a half subtractor, right, or if I want to design a 2-bit multiplier, how will I do, right? And if you are able to come up with the solution, then the goal of this tutorial is done. Okay. So that's all from my side. If you have any question, feel free to ask.
Sir, I have one question, sir. I need some clarification on the slide number 6, the question number 1, sir.
One moment. Slide number 6. The question one. Yes. What clarification you require here?
Sir, actually, in this question, we need to design the binary to gray converter
Yes.
using two 3x8 decoder.
No, no, I've changed actually. So that the question was actually incorrect. Okay. So extremely sorry for that. But yeah, I've changed the question. 1 3:8 decoder and 1 8:3 encoder. Yeah.
Okay, it's very good. Okay. That is my doubt, sir.
I hope this session was helpful to you guys on solving questions and how you solve and you understand the circuit, and how you use multiplexers as a universal gate and use decoder to design circuits, right? So you do the assignments, everybody, right? So I think one deadline is tomorrow, the other deadline is on 31st, right? And I hope you are learning and liking the digital circuits now. Okay. So thank you everyone for joining. Uh, we will sign off for today.